And the problem was the points were starting to fall off the top of the graph. Quite unusual in science, really. In the end, I plotted up all the data and was able to show that the springtime ozone amounts over Halley Station were getting systematically lower year by year. And it was that told an unsuspecting world that there was a link between the declining ozone over Antarctica and the increasing chlorofluorocarbons in the atmosphere.
Hello and welcome to this episode of Beyond the Ice, the podcast from British Antarctic Survey where our polar experts give you the inside track on newsworthy climate science. This week is the 40th anniversary of the discovery of the ozone hole above Antarctica, or more specifically, the anniversary of that all-important scientific paper published in the journal Nature in 1985. It's one of the most important discoveries of the century, and it was made by British Antarctic Survey scientists who were taking routine measurements of ozone at the UK's Halley Research Station on the Brunt ice shelf in Antarctica. That hole in Earth's protective atmospheric layer was caused by human emissions of some very useful but very destructive gases, and the scientific evidence of their impact galvanised one of the most successful global environmental agreements ever created. We could definitely do with a bit of that energy right now. In this episode, I'm bringing you extracts from a fantastic live event hosted by the Royal Geographical Society. We'll hear about the discovery of the ozone hole, how it led to political and industrial action, and what's happening with the ozone hole today. First up, here's BAS meteorologist Jonathan Shanklin. It was John who took the critical ozone readings in Antarctica in the 1980s and realised something was wrong.
Right, hopefully I can press the right buttons. So I'm going to start right at the beginning and answer the question, what is ozone? So in the air that we breathe, there is oxygen molecules comprised of two oxygen atoms. And if you react one oxygen atom with an oxygen molecule, then you have ozone. It's a reactive gas, and if there was too much of it in this room, you'd quite quickly know about it. It can give you asthma attacks, affect your eyes, and so on. But it's mostly high up in the atmosphere. So what we do with the Dobson ozone spectrophotometer is look at two wavelengths of ultraviolet light. One is strongly absorbed by ozone, the other is weakly absorbed. And by looking at the ratio between the two and doing some fairly complicated three-dimensional trigonometry, we can work out how much ozone was present in the atmosphere. And the instrument that we used was designed by a professor of engineering and physics at Oxford University. And in the 1930s, so we're pretty much coming up to the 100th anniversary of the instrument, he designed initially a photographic instrument and then a photoelectric instrument to measure ozone from the ground. And it is still one of the world standards for measuring ozone from the ground. And it was the Royal Society that decided in 1956 that one of Dobson's instruments should be sent to our Halley station in Antarctica for the International Geophysical Year of 57-58. When I first went down there in 1982, I was the junior member of the team, so I was asked to operate one outside. It was only about -10 to -5. It's not terribly cold. The instrument I was using was a brand new one, and one of the reasons for taking it down was just to check that the existing instrument was behaving itself. So my involvement with the Antarctic Survey really started having read natural sciences with a specialism in physics at the Cavendish Laboratory in Cambridge. And so, having graduated, I joined the Antarctic Survey. And initially my role was to process data that had been collected in Antarctica, and I had no idea whatsoever what Antarctica was like. Data came back intermittently via a telex machine in the office, so we could get messages backwards and forwards. It was rather like using text messages these days. You were limited to very short strings, so you dropped characters out in order to try and make things a bit easier. But equally, dropping characters out often meant that things were misinterpreted because the missing characters got put in wrongly. Otherwise, it took a year or more for data to come back. So our ship, in those days it was the RRS Bransfield, would leave the UK in October or so, sail down to the Antarctic, visit a number of Antarctic stations, and then come back to the UK. And we eagerly awaited the packages of scientific data that would come with it. And typically, the ozone measurements were written down on sheets of paper that had set columns. To compute an ozone amount exactly would take maybe 10 minutes using log tables or a slide rule. And basically, along the bottom of this graph is a measure of the time of day, and up the top is the reading from the instrument. And the problem was the points were starting to fall off the top of the graph. So it's literally a question of data falling off the graph, which is quite unusual in science, really. At about this time, there were concerns that the exhaust gases from Concorde and spray cans and foam in upholstery and refrigerants would destroy the ozone layer. And me, being a naive young scientist, thought, what a load of rubbish, that's highly unlikely, isn't it? I know, we've got this open day coming up. I'll put the latest data that I've just analysed on a graph, and people don't need to worry about all of these things. Joe Farman had written a massive report covering all the data from the start of the Halley operations to 1972. And I thought, well, I'll use his data, compare it against the present, and they'll be the same. So I did exactly that, and they weren't the same. So Joe said, I think you better not present that graph, because next year it'll be higher than what I reduced, and you'd look really silly. However, I fortunately wasn't entirely convinced, so was able to slowly work my way back through the 10 years of data. And at about the same time, I wrote a couple of letters. One went to a group that were doing balloon work in the US, and another that was doing satellite work. And if they'd actually bothered to pay any attention to the letters, they would have made the discovery of the ozone hole. So this is another example of luck in science. But I did get a nice letter back from one of them saying, thank you, we're not doing that anymore. In the end, I plotted up all the data and was able to show that the springtime ozone amounts over Halley Station were getting systematically lower year by year. And it was that really forced Joe and Brian and myself into publishing the paper that appeared in Nature, which told an unsuspecting world that there was a link between the declining ozone over Antarctica and the increasing chlorofluorocarbons in the atmosphere. So why were we seeing it over Antarctica? It was all to do with these beautiful clouds that form during the Antarctic winter, where it gets very cold in the center of the ozone layer. And on the surface of those clouds, chemical reactions can take place that convert the chlorine from the chlorofluorocarbons into an active form, so that when the sun comes back in the Antarctic spring, ozone is destroyed at about 1% a day in that central part of the ozone layer. And since the discovery, ozone amounts continued to plummet until the early 90s, and then they bottomed out. And the main reason for them bottoming out was not the Montreal Protocol, but the fact that that valley that I showed you had got to sea level. And once you've got to zero, you can't go any lower. And the bits above and below that valley are not cold enough for those clouds to form, explaining why it's being seen over Antarctica.
The next extract is from Professor John Pyle, who's an atmospheric scientist based at the University of Cambridge. John was one of the 4 co-chairs of the Scientific Assessment Panel for the Montreal Protocol. And in this extract, he talks about the journey to scientific consensus and how that led to political action.
I think it's difficult to overestimate the importance of the paper that was published 40 years ago. It was one of the key geophysical papers of the 20th century. Before the paper was published, there was theory that chlorofluorocarbons, industrial compounds containing chlorine, could get into the atmosphere, could break down in the atmosphere, and could destroy ozone. The paper that we're talking about was the first to actually show that ozone was being destroyed. Where the depletion was happening and the time of the year at which it was happening was a complete surprise to the scientific community, to the atmospheric science community. And it caused a huge amount of work to elucidate exactly what was going on. A huge amount of work that actually probably made massive strides within 5 years of the paper being published. So the theory was that these industrial compounds were very long-lived. They were fine. You could, as John said, you could spray them on your hair or under your armpits. They didn't damage you. They were used in refrigeration and in foam blowing. But if they got high enough in the atmosphere, it was realized that they could be broken down into chlorine atoms. The chlorine atom reacts with ozone and it forms a molecule called chlorine monoxide. So we've destroyed an ozone in going here. The chlorine monoxide can react with atomic oxygen, which is really kind of like another form of ozone, and we can go back to chlorine. So we run around this cycle and we've destroyed a bit of ozone. There isn't very much chlorine, but the point is if we go around this thousands of times, then we can destroy a large amount of ozone. So this was the theory that was put forward in the 1970s. The paper that John has been talking about was the first time that we really got an idea that ozone actually was being destroyed. A huge amount of work followed, as I've said. These are data taken by the Americans in 1987. So 2 years later, they took a big expedition down to Antarctica. They also flew their converted U-2 spy plane, so it flies very high in the atmosphere, in that region where the big bite out of ozone was that John was showing you. They flew from Punta Arenas in Chile at about 62 degrees south, as far south as they could go, and these are data collected in mid-September. And you'll see that the ozone initially is quite high, but as they flew further south into the region where these very low temperatures, where those polar stratospheric clouds might be, we see a big drop-off in the ozone, and it's anti-correlated with chlorine monoxide. So there is a real correlation, or anti-correlation, between these two. If chlorine is high, ozone is going to be low. This was known as the smoking gun. And this paper was published at almost exactly the same time that the Montreal Protocol came into existence. This, I think, convinced the industrialists that actually their compounds were getting into the atmosphere and doing damage. So what happened next? The Montreal Protocol, as I say, was ratified, came into existence in September 1987, and Kofi Annan called it perhaps the single most successful international agreement to date. Really important. There are some key parts of why the Montreal Protocol was successful. First of all, every country in the world eventually ratified the treaty. So the parties are the individual countries. It's universally ratified. The countries themselves have a responsibility to report the production and consumption of ODSs, that's ozone-depleting substances. I might use that acronym occasionally. Decisions are made by consensus. The parties have got to agree. That makes it a slow process, but it also means that once they've agreed, they don't change their mind. Everybody is moving in the same direction, perhaps not as quickly as some people would want. Another key feature of the protocol was the recognition that countries with developing economies needed financial assistance in moving away from CFCs to other compounds or other technologies. And the multilateral fund was set up. To date, more than $4 billion US dollars has been spent by the Multilateral Fund helping those poorer countries with assistance from the countries that contribute to the fund. So what's happened? So we're looking at a graph showing time of, showing year against the amount of chlorine. So more chlorine, worse for ozone. And before the Montreal Protocol, these gases, the abundance of these gases was growing at about 3% per annum. That's the no protocol line. The Montreal Protocol came in 1987. That's shown here. And you can see it's a really modest thing. I used to say to my students, you're driving towards a wall at 100 miles an hour and you think, crikey, I'd better slow down to 80. I mean, that's effectively what was happening. But as the science became more and more convincing, then regulations, amendments to the protocol were made by consensus. Everybody agreed. So here's the London amendment in 1990. Mrs. Thatcher was at this meeting, where it was agreed that CFCs would be completely phased out by the end of the last century. But you can see this growth in the later years of the green curve associated with replacement compounds, which were also ozone destroying, but not quite so much so. And then subsequently, amendments in Copenhagen and Beijing and others have actually brought us down onto a trajectory where the chlorine gases are being removed from the atmosphere. But you can see the lifetime of these gases, some of these gases is long, it's a slow process. Chlorofluorocarbons are now decreasing their abundance in the atmosphere. It takes a long time to remove them, but they're on their way out. We expect to see a concomitant rise slowly in ozone. And finally, where are we today? Well, the CFCs, which are climate gases as well as ozone-depleting gases, were phased out by the end of the last century. There are still one or two minor uses permitted, but essentially they've gone. The HCFCs, which are less potent than the CFCs, there's regulations so that they, between 2030 and 2040, again, will be phased out. And the Kigali Amendment came in 2017 to regulate, again, the last generation of alternatives which weren't ozone-destroying gases, but which were potent greenhouse gases. And that is going to contribute, by the end of this century, something like several tenths of a degree on top of the several tenths of a degree benefit we've also got from CFCs being removed.
This last extract features Professor Lucy Carpenter, who's an atmospheric chemist based at the University of York. Lucy has also led important work for those scientific assessment panels attached to the Montreal Protocol, and she was one of the lead authors of the 2014 and 2018 scientific assessments. Here she is talking about what's happening with the ozone right now.
So John already mentioned the ozone layer. There is a recovery. The Montreal Protocol is working. And we see that both in the phase down of the chlorine and bromine compounds that are controlled by the ozone, by the Montreal Protocol, but now we see that in recovery of ozone as well. It's a little bit trickier for ozone, and so there's a lot more variability in ozone than there are in the ozone-depleting gases, and that's because there are many, many different factors that impact on ozone. So it's quite hard to predict exactly what's going to happen from one ozone hole to the next, 1 year to the next. The middle stratosphere has somewhat weaker recovery, but it's still in line with the observations. And in the lower stratosphere, we have a little bit of a different picture where ozone is not recovering perhaps as we might expect. There is some differences between the models and the observations. Variability seems to have got a little bit worse in the last few years. You can see those really big ups and downs in ozone. So the model agreement overall tells us that the primary influence on these long-term changes in global ozone are due to halogens, but we have variability that's due to other factors. 2021, 2022, and 2023 were all consecutive years where actually the ozone hole was incredibly large. And so here we are on a path to recovery, and yet we are seeing very large ozone holes in recent years. Normally, the ozone hole starts to close by the end of November, but in those years, it didn't start to close until around December. So something was going on in those years, and we think some of those changes, or some of those strange years or anomalous years, were down to atmospheric dynamical changes. And partly that has some relation to climate change. As the climate warms up, there are dynamical changes happening in the atmosphere, which are sometimes quite hard to predict. But there are other exceptional events that happen too, and I think some of these events were quite a surprise to us as scientists, and I think even now, it's hard to say whether actually anyone predicted some of these extreme ozone holes that we saw, especially in 2021. And we think that one of the reasons for that are the enormous wildfires that happened in the Northern Hemisphere in Siberia and in the Southern Hemisphere in Australia in 2019, 2020, and 2021. Those fires were so intense that they lofted huge amounts of smoke and smoke-filled aerosol right up into the stratosphere. Luckily, we have good eyes on not only ozone, but on also some of the chemicals that are involved in ozone depletion, both from surface-based data and also from satellites. And there are various scientific studies that are put forward mechanisms why these wildfires have resulted in additional ozone depletion. You know, we don't always know everything, and I think often as scientists what we try to do is test our models very rigorously against observations. And where they fail, which they are in this case, it tells us something. It tells us that there are missing processes that we don't fully understand. So it's really in this level of detail that we're trying to understand what's happening to ozone, and that helps us to gain greater confidence in our projections in the future. However, the good news is that the ozone layer is still recovering due to the Montreal Protocol. Essentially, if we keep reducing ozone-depleting substances in the way that we are, these exceptional events will have less of an impact on the ozone hole and on the ozone layer. So if we keep following that path, which we expect to do with full compliance with the Montreal Protocol, the ozone hole and the ozone layer will recover. Ozone should recover in mid-latitudes and globally by around the middle part of the century and a few years later in Antarctica. So in around 30 years' time, we should see, when we say recovery, we mean recovery back to 1980 levels, which is the benchmark that's included. So I think that's a good news story in terms of the discovery through to what you can see there is quite severe ozone depletion to that recovery happening over perhaps a generation in many people's lifetime. People, if you're a policymaker, of course it's fantastic. You can point to many, many ways in which the Montreal Protocol is working. You might be asked the question, exactly how well is it working, or exactly what has it avoided so far? It's actually impossible to give an exact answer to that question because, of course, we don't know what the world's trajectory would be without the Montreal Protocol. However, scientists are a game bunch, and they've had a go at this question. In fact, it's thought that essentially if there'd been no Montreal Protocol, by the end of the century, by 2100, about 80% of the total ozone would be destroyed. And that would lead, of course, to a huge increase in the level of dangerous UV radiation. By 2030, that could have led to another couple of million cases of skin cancer per year. And also, John mentioned many of these gases are greenhouse gases. They add to climate forcing, so we may have seen a couple of degrees increase in climate warming by 2100. That would be very significant indeed, coming on top of the increases that we would get from CO2 and other greenhouse gases. So the climate benefit to these Montreal Protocol restrictions is absolutely massive as well, and that's a really key message.
Thank you for listening to this episode of Beyond the Ice. If this whetted your appetite and you want to dive into this topic with more detail and significantly more graphs, you can watch the full presentations and the panel discussion on the Royal Geographical Society website. If you enjoyed this episode, why not recommend the podcast to friends or leave us a review on your preferred podcast platform? Thanks for listening. See you next time.